Thanks for the introduction. Thanks for the invitation. Can everyone hear me in the back? It's fine? All right. Second question, can everyone see the beautiful red color here? Okay. So, I might show a couple of green looking flames. If you want to see the red version of them, that's going to be probably better seen on the 200. All right, so like I said, thank you very much for the invitation. I've very much enjoyed the warm weather here. By contrast, in Ithaca, upstate New York, it actually snowed last week, which is a bit early compared to what I've experienced in the past few years, but yeah. I'll put it a bit. Okay, so I wanted to try to follow as much as possible the theme of the EPIC seminar series, so process enabling, process innovation. So what I did is I reworked my title to include the word enabling and the word process. So I tried to convince you that it's still relevant to process development and process design. It's fairly upstream of that. We are looking at a fairly fundamental series of studies that we've done of turbulent liquid gas flows. Clearly, we're going to focus on the computational aspects, so I'll be talking about simulations. I don't do experiments. I think they're cool. If you do them, that's great. But that's all I do. And most of what we're going to talk about will involve turbulence at some level. Okay, so let's start with some quick acknowledgements. A lot of what I'm going to show comes from a couple of PhD theses, and probably the most relevant one is by Mark Oates, who graduated a year ago from my group. So I'm just basically stealing all this stuff and presenting it for him. And his professor from the State University. So I'm hoping that this had snow before we had snow in that. Funding comes from mixed sources. There's some industrial funding that has led to this work, and also some more and some NSF funding as well. So since we're going to show some fairly large-scale simulations, I should acknowledge federal computational resources. We are running on some of the largest supercomputers in the world, so I'm pretty glad that we have access to those. Some of them are at Lawrence Livermore, we've run on Sequoia and Sierra. Some of them are actually Sequoia, wait, one of the two, right? I think some of this, I might have overstated that. This work I think was only on either Sierras. We've used extensively the Kraken XC machine and more recently Sandy. We've been making use of Titan at Oak Ridge, and more recently the Mira system at Argonne. All right, so let's see how the colors look. All right, so we work in my group mostly on computational, well, we do exclusively computational work, focusing on thermal fluid flows. So we're interested in modeling flows, typically complex flows that involve multiple phases, interfaces, and chemical reactions. We are also making as much as possible use of massively powered computing. So we kind of like just brute forcing solutions to these complex problems. So a couple of things I'm not going to talk about. We do a lot of particle laden flows. I don't know why I chose this movie because it's probably the most boring one, but this shows the sand grains in water flow at the bottom of a pipe. And we're looking here at the entrainment of the top of the sediment layer as the fluid. But we've done a lot of work with cluster formation and risers and fluid aspect reactors, bubble formation, things like that. This is another particle-laden flow model, even though here I'm not showing the particles. This is the riser reactor, so we're looking at two. And in this tube, we're injecting gas at the bottom. There's particles that are catalytic particles that are going to be entrained with this pneumatic transport of those particles. They're being pushed up. And when these particles encounter biomass vapor, a certain type of biomass vapor, it will convert that to another chemical species. This is called biomass vapor break. And so we're interested in looking at what would happen in a system like that, where we simply have particles that are being pushed up by flow. And that's it. Gravity bringing them down and nothing else. And what it turns out is that particles tend to form clusters. They come together, form clumps, denser regions. They do that on their own. It's a spontaneous process. And they start forming along the hemodynamic boundary layers in the system. And that leads to strong inabilities that they lead to very much non-trivial flows, as well as a fairly significant reduction in the conversion rates of that reactor. And that's, we're looking here at the turbulent flame. This is a simulation of the so-called 70ID carbon. We're looking at fuel injected here in the middle. There's a pilot flame with a small flame in an annular region around the jet string, and then there's the oxidizer around, and we're looking at formations. And this thing I'm not talking about for now because we're going to talk about it in a lot more details. This is a liquid atomization process. So we're looking at a liquid jet breaking up into drops and foams. So why are we interested in those things? Well, we're interested in that because in general, multiphase flows are everywhere. They're important for most of the industrial processes that we have out there, anything that involves energy conversion, any type of conversion process, any type of manufacturing process, it's just ubiquitous, it's everywhere. So that's something that we need to understand. It's also, beyond engineering problems, a very relevant type of a process in environmental flows as well. For example, the turbulent two-phase flow that takes place in breaking waves is a limiting process for the rate of transfer of various quantities across the atmosphere and the ocean. If we want to model rain, we need to be able to deal with large collection of droplets moving into turbulent flow, coalescing, becoming large enough that they can eventually fall. This is again a turbulent two-phase flow process. So all those things, and here I should say, so this is so this is anyway, this is a model aircraft gas turbine combustion chamber flame. So we're looking at anything being injected, burning, and this is your fairly standard bubble column, and what you would do in the type of transformation process. So if we want to zoom in on one specific motivation, I'll use combustion as a relevant grand challenge. I'd argue that we want to improve combustion efficiency while lowering emission in the context in which fuel flexibility is becoming more and more important. So I'm trying to illustrate that here by the fact that the efficiency, projected efficiency of cars all over the world is, well, the efficiency is going up, but the consumption of fuel per 100 kilometers is going down everywhere, and that's driven by regulation, as well as progress in understanding of systems. And at the same time, we're actively exploring alternative ways of generating liquid fuels that are usable. So we're interested in looking at how we can convert different types of biomass products, including algaes and corn starch and stuff like that, and convert that into a usable liquid fuel that we can then burn in our engine. If we combine all this together, this obviously will have a fantastic impact, positive impact on the environment, but this is a very significant problem because now we're basically saying that we need to optimize the combustion process, which is a complex multi-phase non-isothermal, reactive, explosively reactive process, with the fact that the type of fuel is changing, so we're not even sure exactly what we need to optimize and what are the value conditions that our problem. All right, so let's consider this very continuing thing and think about this a little bit more. So by the way, this image comes from Roman's group at Stanford. When I started my PhD, I was working on doing a library simulation of that film. So I've kind of stayed with that image for a while, and it's been ingrained in my brain. I would argue that if you want to work on combustion and have a positive impact on combustion processes, at least part of the key to that is going to be in the liquid-gas interaction, in the liquid atomization process. So fuel injection is critical to the system. Here we're injecting helium, which has this really weird greenish tints, but it's actually the case. It is kind of greenish because of the lighting. We're getting this blue hue here because of OH radicals, and then we're putting soot, and that soot is going to be this yellowish color. All this is turbulent, all this is swirling. We have a big recirculation region here. There's a region here with the flow actually going back inside. But this is a very complex flow pattern, heavy, turbulent, highly multi-scale. But it turns out, we have some decent understanding of the combustion process in this. We have okay models of the turbulent combustion process. When I started my PhD, I started running simulations of that, and I realized I could get pretty much any answer I wanted in terms of, let's say, one metric, it's the temperature of the exit. Why is it important? Well, if the temperature is too high, we're going to burn the turbine blades, and we're not going to have a working engine. So I could get pretty much any answer by changing the properties of the rockets that was injected. So I was modeling this liquid injection in the form of a bunch of little point particles with a certain size, a certain temperature, and it was forming them as they were going into the domain. And like I said, I could get pretty much any answer I wanted by changing the boundary conditions here, which were not provided experimentally. So I thought, well, this is a problem. We really need to figure out a first principle-based approach to predict the outcome of this fuel injection process. Or else there's no real point in improving our combustion models if we still have to somehow run the entire experiment in order to figure out what is the drop size. So at this point, I would argue that we don't know exactly, we even say we don't know at all what controls drop size distribution in a system like that. We have some ideas of what possible mechanisms can lead to the formation of drops, but we don't know which mechanism is going to be dominant in a given configuration. Given flow configuration. And we typically do not have predicted first principle-based models capable of telling us what to expect. If we change the flow rate, if we change the nature of the fuel, let's say we go from a classical petroleum-based fuel to a biomass, a bio-derived fuel, we're going to change the viscosity, the surface tension, density, we're going to have different parameters. We, at this point, have no models that are going to be able to tell us what we should expect in terms of drop size. If we don't know the drop size, we don't know the drop velocity, we don't know the drop distribution, we don't know exactly how the combustion process is going to look like, we don't know exactly what type of routes we're going to be forming, we're not going to know exactly the efficiency of the system, we essentially don't know anything. Alright, so hopefully I've convinced you that it's important to improve the way we model multi-phase processes. I'll argue, however, that this is a challenging task, and I'll make a few arguments for that. One is that clearly a liquid gas flow is discontinuous in nature. In fact, that we have within our computational domain, if you look at that from a computational perspective, we have to deal with an interface that represents a discontinuity between the two phases. That interface is extremely thin, and essentially for all intents and purposes for us from the perspective of engineering flows, it's going to be a discontinuity in our system. It's going to be infinitely thin. It will lead to a surface tension force. So we have a singular force that exists at the discontinuous interface, and we have to deal with potentially ratios of density across that interface of the order of 1,000. So that means that the stuff on one side is much, much heavier than the stuff on the other side, and it can induce very large flows by just very minor motion. We're going to have to deal with significant pressure variations when we move our liquid around. This guy is actually not, so this guy is using more the fact that there's a difference in density. So that's surface tension. Surface tension here on that scale is not really helping this guy float that much. It's really just inertial forces that are helping. We also have to deal with the fact that this is a highly multi-scale type of problem that we set for ourselves. We care about spray formation, so we care about droplets. So droplets are going to be typically of the order of maybe 10, 20, 30 micron in size. So we care about those drops because we want to know, how big they are, how many they are, and how fast they're moving. But we also care about the scales developing on the scale of the injector. We need to know the flow pattern coming out of the fuel injector. And that means that we have typically several orders of magnitude difference between the larger circuit scale and the small circuit visualization scale. And the topology changes that take place in the atomization process, so breaking of structures, happens everywhere all the time, and they're typically very, very catastrophic in nature. For example, here we're looking at a very weird configuration. You have this one balloon being here and creating this backward jet that forms this very cool looking helicoidal instability that then leads to this mushroom shape at the top that inflates into a little bag. So this undergoes bag breakup. You can imagine, we're going from this large scale jet coming out of that one balloon to incredibly tiny droplets just because we're breaking the film that was inflated like that. This is going to be an extremely challenging problem to build. And all this is happening in a turbulent environment, which also leads naturally to many states. And then finally, another aspect is that typically we have those multi-physics types and type of environments. So we have multi-scale, multiple phases, but also multiple types of physics. For example, you might have to deal with early interfaces, the presence of surfactants. I guess this guy was supposed to be the simplification of early interfaces. We might have to deal with non-isothermal processes, non-dirty flows, phase change for critical effects. And one thing that we'll talk about very soon is electrostatic effects. Okay. So we might have additional physics yields. And as a result of all this, it's difficult to run experiments on the gas flows, especially optimizing gas flows. They're also difficult to model accurately. I would argue, however, that we have the opportunity to use the growing computational resources available to us to brute force our way through this problem and use computations as a discovery tool. So if we run large enough simulations, we can generate data that help us understand what controls, what aspects of this flow is critical. We have growing computational resources here. This is your typical bit of flux as a function of time. Over the years, we've increased the size of computational resources available pretty much linearly in this class, in this lockdown. So we've stuck to a pretty decent exponential growth. So we're getting to the point where it's conceivable to actually just say, hey, well, we know the isotopes, we know we have these continuities, we know the parameters of the two fluids. Let's just solve everything. We know the equations. We have this chance where we actually have a complete mathematical representation of the problem at hand. Let's just come up with a solution computationally and see what we can learn from it. And I would argue that from data sets like that can be generated in the spirit, we can then help guide the development and produce all the models that could then be used in generating design data. Right? So I think this is relevant to processing data. All right, so in terms of methodology, there's a lot to be said that I had to make some choices. So I thought that you might not be interested in saying too much numerics on Friday afternoon. But I'm sorry, I'm going to still show you some numerics on the Friday afternoon. So you have to be patient. But I decided to focus on one aspect that I think is kind of cool. It works out in a fairly neat way and that doesn't necessarily require too much time to explain. So I'm going to focus on that thing and kind of ignore the rest. So that's kind of the slide where I provide a bit of context and talk a bit about the rest. So, okay, simulating two-phase flows is something that's been around for a while. So we have many methods and codes out there to do computational fluid dynamics, but most of them have been focused on single-phase flows. We want to augment that with what what's necessary to deal with present interfaces. I would argue that there's really two key components that need to be handled. One is that we need to figure out the location of the liquid-gas interface. So we need some methodology for keeping track of where we go from one phase to another. And there's different methods for that. I would argue that probably the three most commonly found are what we call the level set method, the deployment fluid method, and the flow tracking method. The level set method introduces an auxiliary scalar field. It defines such that one of its isosurfaces coincides with the interface. And then we transport that field such that the interface still coincides with that isosurface. So we're using this auxiliary function as a pure mathematical tool to help us move into it. It's a very neat method. It works really well. It's simple. At least conceptually, it's simple. In terms of implementation, it's simple. It has limitations. I decided to not focus on what I think are the limitations, because depending on what problem is of interest to you, what might seem like a limitation to me might not be a limitation to you. So I thought I would focus on what I think are the best advantages of the methods. You can see, that I've tried to claim that this one method was not good, and I had someone in the audience who was very important and had written a paper on that and told me, that's not good. So this is you know from experience. I'll only focus on the positive aspects. So level set is a simple method to pick up and implement, and it works well. Volume of fluid, the idea is you're going to keep track within each cell of how much liquid is contained in that cell. So you're going to compute what is the fraction of the cell that's contained in liquid. It might be 1 if it's 100%, 0 if it's 0%, and 0.5 if you have half your cell full of liquid. The main advantage that I see in that method, in addition to the fact that it works well, is that it's naturally a method that will give you relations. So you'll be able to write something that, strictly speaking, will conserve the amount of liquid you have. If you have a drop, you can move it around, you're not going to see this drop shrink or grow, because you're keeping track of how much of this you have. From tracking corresponds to kind of maybe more natural approach where you would say, I'm solving my flow equations on mesh. Typically, that's what we do. Let's just introduce an additional mesh to keep track of where the liquid gas is. So we'll just have a mesh on our surface and deform that mesh to keep track of where it is. It tends to be very accurate. So that's one aspect. And for this, I'll say that we'll focus here on volume fluid. We've done a lot of work on level sets as well. I haven't really done too much in contracting, but here we'll talk about it. To me, the second aspect is that we need some way of telling a flow solver that there is an interface at a certain location, and that interface leads to a discontinuous density, discontinuous viscosity, discontinuous pressure, etc., etc. So we need some way of telling our flow solver that it's actually solving two different equations across interfaces. A lot of people, maybe 20 years from now, we're really focusing on what we're doing now, diffuse interface models where we have a smooth transition from one phase to the other, which is an acceptable approach, provided you can say something small about what this diffuse region means, knowing that the two phases are immiscible typically. More and more recent years, we've seen short interface models being proposed where we have true discontinuities within our flow. And here, this is what we're going to focus. All right, so I thought we should start, since I'm going to show you a little bit of numerics, I thought we should start from the very basic idea to make sure that everyone follows. We're going to start with a really cool looking image of a liquid gas flow. That's probably one of the most well-known image of an atomization process out there. This was published 12 years ago. Coming from France, from a guy called Philippe Marmoton, who spent his PhD taking really cool pictures like that. So this shows a liquid water flow. It's a round jet going from left to right. And around it, there's a very thin angular co-flow of gas that's fairly high speed in comparison. So this is moving slowly, and here around it, as you can see, there's an airflow that's pretty fast. This leads to the development of a streamwise instability that's, for those of you who are well versed in fluid mechanics, say that this is Kelvin Amos time instability about. After that, we end up developing radial instability. Okay, so you see the development of those ligaments and this crest becomes uneven. This other pictures from the side I didn't show. This is due to radial instability, and then you start pulling ligaments because they have to surround the gas flow. And those break due to a radial plateau instability. But that's just a very pretty picture. Let's make it good. So if we have in our computational domain a region that's liquid, a region that's gas, we're going to simply define the liquid distribution function, the function that tells us an indication whether we're liquid or gas. That's just simply a function that's a Heaviside type distribution. Okay. That's not something that's very convenient for us to use because it's a distribution. This is not convenient as a smooth function to work with. So we're going to say that if we have a computational cell here, we're going to acknowledge the fact that it contains a region that's gas, a region that's liquid, and we're going to say that maybe we're going to simply worry about the zeros-order moment of that distribution function within that cell. So we're going to simply volume average it over our computational cell. And we're going to call that alpha in cell I at time t. And we're going to say that this guy is simply our liquid volume fraction. Okay, so that's the volume average of this liquid distribution function. Now, from that information, you might say, haven't we given up a lot? And yes, we've given up pretty much all knowledge of distribution of liquid, except on the cell-to-cell basis. But within the cell, we've lost all the information. So we're going to need to make an attempt at recovering some of that information. So this takes the form of what we call a piecewise linear interface calculation. This is something I was proposed a number of years ago. I'm just presenting other people's work here. The idea is we're going to say in cell, we're going to assume that we have obtained from the solution of our equation, we're going to assume that we know how much liquid we have. And in addition, and that's kind of a stretch, I'm skipping a number of things there, assume you also know the orientation of the elements. And that's a tricky question. But I'll argue that it's possible to obtain an idea of validity in the basic orientation if you have enough information regarding what the volume fraction is in the surrounding area around the cell. So, looking at ourselves, the volume fraction, normal orientation, we'll make the assumption that the interface within our cell is planar. From that, it's actually sufficient to solve this as a purely geometric problem. We're going to simply compute where this interface should be located such that it is perpendicular to this normal vector and such that the volume under this interface integrates to 10% of the total volume available. That's easy to do, and this is analytical if you're working with an exact equal cell. If you're working with a computational cell that's more complex than that, it's not analytical, it's more complicated, but it can still, it's a nonlinear problem that's very small, but we can solve this iteratively and we will obtain solution. So this, you can think of that as a model closure that allows us, within this cell, to take the zero-order moment information, which is our volume fraction field alpha, and reconstruct from it what is the internal distribution of interface. The big issue with this is that this representation in the form of a little chunk of line is discontinuous. From cell to cell, we're going to have this little chunk so that we can pick the discontinuous and will not nicely connect. So, one second. I should check that approach is done. So, how do you transport a volume fraction? Well, it turns out a volume fraction is a discontinuous quantity. And transporting a discontinuous quantity is problematic. And if we just use naive methods, roll here of some sort, we'll diffuse it out, and we won't be able to maintain this discontinuous nature. We'll have a bunch of cells where we don't know how much liquid or gas we have. We'll have some mixture of both. If we use a high-order scheme, we can maintain this discontinuous nature a lot better, but then we'll overshoot and undershoot. So we'll create regions that have more than 100% liquid or less than 0% liquid, which is not very convenient. So instead, we need to propose an alternative approach, and the approach we're going to use is going to be in nature. So I'm going to first recast the problem into a simple circulation problem. So let's say I want to know what alpha is in that cell at time t plus 1. I would argue that I simply need to figure out how much is fluxing in and out of each cell. And then I can simply obtain the new volume fraction from the knowledge of the old volume fraction and the knowledge of how much liquid is left or enter the cell. Okay, so we'll take a cell, and what we'll do is we'll take the cell face, and we'll in a geometric sense, emit what we call a strict tube. So we'll just take that face and move it back in time to where, in a Lagrangian sense, if it were fluid particle, what would have been in the past, such that this line over our time step should deform into that straight line. Okay? So I've created a straight tube that corresponds to the region by volume that has been swept by fluid molecules that correspond to that cell face during the time step. Right? So now that I have a straight tube, well, obviously I didn't tell you how we're going to generate it, but from the knowledge of that straight tube, the other thing I need to know is to figure out how much liquid I have in that straight tube, which I can compute because I have a split reconstruction of the interface. If I know how much liquid I have in that straight tube, I know exactly how much liquid is entering through that face. Okay? So that's the equation we're going to follow. The equation followed by this little point here is just a pure Lagrangian equation. I'm taking that point and taking it back in time according to the flow velocity. So that's now the time we need to do. And so how do I generate the geometry of this? Well, it turns out this is not a particularly new idea. People have been looking at that for a while. It started 40 years ago. Where people said, well, if we can get a 1D approximation of our straight tube, that would be great. So they just took their face and then moved it back in time in the direction normal to the face. And they looked at the volume swept and how much liquid was in the tube. That was easy to implement. It worked terribly. People then realized, all right, we need to account for the fact that the flow doesn't go normally through the face. It actually has an angle. It goes in whatever direction the flow is going. And so they accounted for the fact that those volumes here had to be inclined, but then they generated this in a way that neighboring strict tubes could overlap. If you're overlapping strict tubes, you end up with a region of the flow that's going to be fluxed twice. Once above through the face at the top, once below through the face at the bottom. You're not going to be conservative if you do that. That doesn't work well either. And people realized that and fixed that in 2D. People said, all right, we're going to need to fix that to plug that in 3D. And we realized, well, it's complicated. So we'll now for, again, some overlap between strict tubes that are connected through that corners. So again, this is not preserved. So what Marco a few years ago did was they said, well, let's just wipe the wheel. Let's simply need to take our cell vertices and those corner points and make sure that they move consistently, no matter what strict tube they're part of. They need to essentially remap those cell faces into, in a Lagrangian sense, what they would have looked like in the past had they been an actual material fluid surface. And then that's going to give us our usable strict tube. At 3D, that can be made discretely conservative. I will argue it is inherently discretely conservative, but that can be modified to be discretely conservative. It also has the advantage of being balanced, so we'll never get more than 100% liquid or less than 0% liquid. So it has a number of advantages. But it's pretty complicated. Why is that? Well, that's kind of a naive idea of what this would look like. You just take this space and you take it back in time, now it looks like almost like a cube, everything is easy. But in real life, this point could be moving to the right, this point to the left, this point to the left, this point to the right, such that this might be the shape that the strict tube takes. You'll have cross geometries and negative volumes, and it's going to be a mess. So we need a way of dealing with it. It turns out that's not particularly complicated, so I'll just focus on this one example to show you this for as well. If we just stick to 2D, and I label my face AB, then let's say that the generated strict tube in this very simple configuration is ABCD. We're just going to do two things. The first thing we're going to do is we're going to break it. We're going to assume all lines are straight lines, so we're going to deal with a purely linear representation of all that, which should give us second order accuracy. And in addition, we're going to deal only with simplices. A simplex in 2D is a triangle, so we're going to represent our strict tube as a collection of triangles. That's the constraints we're getting ourselves. Straight lines, triangles. And then we're going to simply introduce an ordering convention. We're going to say that our triangles are always going to be named A, B, C, and A, C, D. And if they're oriented positively according to y and rule, we'll give them a plus sign. If not, we'll give them a minus sign. So that gives us in the positive area, I guess, I put in 1, 2, 4, and 3D for that guy, and that sums up to the appropriate order for that guy. So that's good. If now we go to that configuration where B has moved to the right and A to the left, that's the configuration we get. A, B, C, according to the right hand rule, is now a negative object. A, C, D is still a positive object, where it appears double counting this region that should not be part, this region here should not be part of our fluxing volume, yet it is covered by both triangles, but once with a plus, once with a minus. We're double counting, but canceling those errors, we end up with a very simple representation that allows us to say that indeed that part here, limited by this line here, has moved with a minus sign, so this is going to the left of the face, and that part here is assigned with a plus sign, so it's going to the right. We've successfully, with second order accuracy, dealt with a representation of flow in and out and simultaneous flow of events.
Quick clarification. These schemes you are storing the velocities at the corner points?
We are bringing our velocities to the corner points. We're not, so the scheme we use is staggered. So we have a velocity at the faces, the center of the faces. That's typically where we store it, but through interpolation, we can bring it to the corners. We have to do the interpolation to bring it there, but we're going after second order accuracy here and conservation. Interpolation is not an issue.
So the interpolated velocity is the corner that you use
in the calculation of the street tubes, exactly. All right, so I would argue that this looks like a simple example. It turns out this idea of taking a complex arbitrary street tube, breaking it into simplices, so in 3D that would be breaking it up into tetrahedra, and then specifying a unique, well-chosen order for the points to define the sign for those objects is sufficient to deal with all possible complex, overlapping, crossing geometries. So that's what we've done, and the conclusion is that that works well. So I'm not going to hopefully I'm not going to use that too much. A couple of tests, we've formed a circle, which is exciting. So imagine it's a drop, and precision and bounding cells are 0, so we cannot push a direction. So it's a very stable scheme. The big problem, I'm not really mentioning it, I've been giving you all the information, but that's really meaningless without context. It's pretty expensive, so that's kind of the prospect. Okay, so I won't go into much more detail with the scheme, but once you've created that, you know how much liquid you have at the beginning of the time step. You know how much liquid you have at the end. And you know how much liquid went through each phase. You can combine all this to help you build a conservative transport scheme for any other discontinuous quantity that's discontinuous because of the presence of the capacity. So you can now transport momentum, the momentum of the fluid, which is a discontinuous quantity, in the same way. You can transport a scalar that is only existing in the liquid, not in the gas. So a concentration of something in the liquid in a way that's conservative, even though your mesh is being cut arbitrarily by the You can be second order accurate and conservative for any other type of transport. And here this is an example that's really fully chosen representation of that. But what this is a circle that's being transported in a domain, and we're tying a scalar to that circle, and we're just assigning it a Gaussian distribution. So we have a scalar field that's a Gaussian that's being moved around, and diffusing as well, that's being moved around by us moving the circle. And you can see we have an exact solution for it, and again, you get some other names. And this is again another conservation test. It's so this is usually where the computer practice. Let's see if it makes it through. Yeah, all right. Good enough. So we've used this for to study a number of configurations. Try to organize them in a weird way here, and moving around by increasing complexity. So we've looked at simplicity of simple velocity over shear interface. We've looked at various stabilities of the formation of the breakup of the ligaments. We've looked at rising bubbles. We've looked at male crown formation. We've looked at the turbulent planar jet. This is an air gas configuration, so we have a liquid layer that's being atomized by running a high-speed gas flow on top of it. We've looked at, the timing for this one is good. We've looked at the simple round jet of liquid into quasi gas. This is what we'll start. So this is probably one of the biggest simulations we've ever done. This was a couple of billion cells on 12,000 floors. So we've looked at the atomization process of this. So then we've added to the WISDAMs, those ideas. We've added Emos boundaries such that we could look at a complex injector. So here we're looking at a swirl atomizer where it gets the formation of this air core in the center of the swirl atomizer. So we're just spinning liquid and gas is re-entering from the middle. And then we went all the way up to a realistic General Electric's injector, which is shown here. And I don't even think you can see the interface in this, but there's also a pressure swirl injector. So anyway, yeah. Okay, very good question. Breakup is inherently modeled through opportune numerical errors. That's the truth of it. So when we don't have enough resolution, we see topology changes because our representation is based on figuring out how much liquid is contained in our cells. This is volume of fluid, and so I would argue that click piecewise interface reconstruction that assumes that we have a single plane interface in each cell is our breakup model. If we don't have enough liquid, and our normal is poorly calculated, instead of, you could imagine if I have two interfaces that come close together, click is simply wrong. We should have our two interfaces. We should have two interfaces represented in the cell. We don't do that. Instead, we typically put a single one, and we'll put it perpendicular.
Therefore, considerations mesh defining sets.
Absolutely.
Criteria, if you will.
Absolutely. It's the mesh that ultimately decides when we see the privilege. It seems terrible, but it's not that bad. It is terrible if we're looking at a thin film. So if we're bringing two interfaces close together, it's entirely going to be the mesh that will decide when this breaks. So I would argue that with those methodologies, we're not capable of simulating backbreaking. This very complex, weird-looking balloon that was breaking into this umbrella-shaped thing. Those technologies are going to be very poor at simulating.
So it works for 3D, but it doesn't actually work for 2D.
Yeah, 2D is problematic because 2D doesn't have an inherent process that accelerates the breakup. If you have a 3D ligament, pulling of that ligament will give rise to the so-called radial plateau instability that will exponentially increase the rate at which the liquid is being pulled. And as a result, it doesn't really matter how much of it we resolve, we'll kind of get the same answer. Past a certain level of resolution, our breakup process will become dependent on resolution. And because of that, we can break up a ligament with reasonable confidence. But we can't really break up a film with confidence. So that's really an excellent question. There's still a lot of work that would have to be performed to deal with film draining and not, a lot of people have looked at that, but how to model that in the context of those type of simulation. All right, so let me skip some of that. So this is some example of validation. We've looked at, we have historical data for some of those simulations. Hopefully I can see that it's qualitatively that those things look very similar. We've looked at drop size distributions, we've looked at penetration. We have looked at very relevant flows for a different purpose. And that is the case of the liquid jet and cross flow. So here we have a cross flow going from left to right. And we're injecting liquid in the system. The liquid is bending, breaking, performing wing drops. We've compared at 50 diameters here the drop velocity as well as the so-called SMD, subtle mean diameter, is a measure of the mean diameter. And as you cannot see at all here, it can work, it's not perfect, but there's also a lot of uncertainty with experimental data. So we're kind of happy to simply be on the same color scheme. We're excited to see that. a more easy thing for us to look at, we've changed the shape of the nozzle used to inject the liquid, and we've been able to compare the penetration of the liquid. So this nozzle tends to favor a laminar jet, at least initially, and the red line here, the green line, the red color line here is the experimental measured penetration. And we're reasonably close to that. In the turbulent case, the jet here comes out turbulent. It has more turbulent kinetic energy. It's more capable of penetrating. It tends to go straighter. And we're also reasonably well following the experimental duration of penetration. All right, I wanted to conclude here. I'm already done. Is that okay? So I'll give you 1 minute because this should have passed. I wanted to show something about electrohydrodynamic atomization. I've talked about modeling novel processes. There's nothing novel about it. Some people have been injecting fuel for a long time. There's nothing novel here. But starting here, we're starting to look at novel processes. People have started thinking about what would happen if you were to inject electric charges within the liquid in order to use the natural flow portion within the liquid to help break up this liquid. That's called EHD atomization. People have shown that if you have a kerosene jet at low velocity, you won't see any breakup. That's actually with kerosene. Or if you introduce charges in here, you can see breakup. The charge experimentally that it has to happen. Here's a slide of grades. Here's a slide of parameters. The important thing is we're implementing that within the computational framework. And we are able to show, so this movie is a bit disappointing because it's very short. But the uncharged case, even in the presence of turbulence, which was not present in the picture I showed, doesn't show any breakup. It would happen probably further downstream. But the charged case here does show breakup. Now, if we compare with what we can compare, we're going to see that, so this is not the same experiment. This is an X-ray of different rounds of the jet, but that reasonably similar parameters. We see a breakable interface, nothing happens, that kind of corresponds to what we would expect in a ambient pressure, high density liquid going at reasonably low values. The charge conditions now, we have experiments for that, we have some data, and well, we have some current data that we have also in photographs. If we build a simulation domain to the scale, we can see that it seems that at least the cone angle that starts to be from here kind of corresponds. The onset of the opening of the thing does seem to kind of correspond. The predominance of outward radially oriented ligaments also seems to correspond kind of with what we're saying. So we're pretty excited to see that there's at least some correspondence between the two. The other thing, though, is that we can say lots about the very detail of the stroke. For example, we can say where the charges are located. The charges are bound to drift within the simulation. They will move towards the surface. If you give it enough time, they will all be at the surface. Turns out that's true. It's way too fast. They will not have time to relax at the surface. So we'll end up with drops outside that will have slightly larger charge concentration, and an inner core that will have somewhat lower charge concentration. If we want to use the presence of the charges to help us steer the spray through external control, for example, which is something that we're starting to look at, we will need to know where, how much charge is contained in the dot. So that's something that we're really excited about, and that's certainly a novel process. That's something that's being looked at to help improve this process of fuel reduction. And that was, so I almost go through that. Yeah, I don't know. Check those rules. Anyway. All right, so thank you very much for your attention. Sorry for being a little long. All right, so any questions?
So in the twin steam are really geometry, and if you differentiate some sort of, integrated dimensions, type of motions, now that we know that it's interface that you want to construct.
So the short answer, yes. people had thought of Blick too much as a computational tool. I've started to think about it more as a model closure. It's the closure that we use to reconstruct our distribution from the non-coded zero-sum numbers. So in the context of method of moments, I think we should think of that really as a closure method. And in that sense, if we can put more physics into that, all the better. I think it's going to be reasonable. If you were to know, for example, that your order is over, you could argue that Blick is not the right solution. Maybe a proper solution to the problem of where the interface is located is by sprinkling and distributing little spherical polygons. You could say that's a circumstantial model. You could say, well, breakup has happened, but since we're not capturing it on proper scales, we should use a model that tells us what we expect locally the drop size distribution should be. So you could really think of, for example, doing field modeling, where once you fall below resolution, instead of just breaking the interface, you give up on Blick. You say, well, I'm not resolving locally, I need another representation of my interface, maybe in the form of droplets, many droplets. And suddenly you would be able to do something like that, maybe use more confidence. So yeah, I agree. I think there's an opportunity for modeling.
You're looking at the top position now, you registry the simulation in order to get the droplet size distribution. Now it's going to do that. So did you find something that is active, or just the result of that the whole process is?
So that's kind of actually my very last point here. When they are actively working on adding phase change to our models, we have already the combustion capability in our computational framework. So we know how to burn stuff in the gas phase, and we know how to atomize. And that's done within the same code. We're working on dealing with space change. So allowing for the interface to receive, the mass to be transferred across the interface to the other phase, and then we'd like to actually burn those drops. I think we should be able to do that within the same code. Well, under heavy assumptions, so we're doing enough Reynolds numbers, we're doing enough Weber numbers for conditions that are easy enough. Yes, I think we can trust what we're doing reasonably well. We're still actively working on validating. I haven't shown a lot of validation. I guess I skipped through a number of validation slides. We are working with experimentalists to try to do more validation. It's difficult to find good atomization data sets because experimentalists naturally will tend to work in conditions that are ambient pressure with water and air, which leads to high density ratios. Those high density ratios have nothing to do with the atomization processes that we see in pressurized environments. So it's difficult to really do detailed validation knowing the presence of this huge gap. But we work with what we can. So we do compare drop sizes coming out of water atomizing. For realistic conditions, extremely high pressure, high velocity, liquid jets, extremely complex geometries, weather models. This is mostly in the realm of not quite but close to DNS. DNS, the concept of direct numerical simulation is simply ill-defined for those types of nodes. But we know that simply the topology change event is not contained within any scope, so what does it mean to do direct numerical simulation? But that's another problem. If the Ramos and Weber numbers are low enough, we can resolve all Ramos skills here. If it's too high, we cannot. We need models that would have to be knowledgeable about the physics of turbulence around interfaces. That's what we're working on heavily. That doesn't really exist. So we're still working this toward problem. Right. One last question. Are they interfacing? Oh, the trunk. I'm sorry. Oh, yeah. It's a tough problem. It's a problem that we've avoided by doing. We have have some knowledge. So the guy who did the experiment is called Trevor. Is in the UK. Is published some really cool stuff. Their injector is complex. So they have a charge injection system. So the outer rim of the injector has a certain potential, and then we have a needle which is at a different potential. This is a very small injector. You don't need a huge power to generate enormous electric fields. That leads to charge transfer from the needle to the lumen. At least that's what we believe. There might be some dissociation happening. We're not entirely sure whether the class of charge.
That's not included.
It is not included. So what we're doing is we're saying it is too complex for us to deal with because we have no experimental data on that process itself. So what we're assuming is that they have a uniform volumetric distribution of charges coming into this, along with salinity. So the liquid comes in with a uniform charge density of something.
And the environment basically the domain within which the injection occurs, electric fields.
So we have a box around it that is rounded.
So you're around the box.
Yeah, we're rounding the box, and then that's it. There's no. We're assuming that there's no charge transfer in the gas. And
Charge is redistributed within the filaments, both because of the fluid mechanics, but also because of the electrostatics.
Correct. So we have drift with respect to the surrounding uncharged fluid molecules, and we have also simple transport. By far, the drift is minimal compared to the convection through fluid mechanics. And then what we have is a discontinuity of the permittivity between the liquid and the gas, which leads to the development of an external stress at the interface, which leads to an additional pressure jump that adds to the surface tension driven pressure jump. So there's some non-trivial mechanics to play on this.
Elementary structure is driven by basically charge of the two ends of the
Yeah, so we don't see those radial ligaments in any other simulation. So we think that this is absolutely, this structure here, we think that this is just because those structures have been pulled away from one another and that the force leads to this just big broken.
Which turbulence model do you use?
I'm sorry?
Which turbulence model?
There's no turbulence model. This is direct microscope. We're resolving all scales.
And how many mesh?
This is not huge. The round summer here is fairly low. This is a couple thousand. The round summer is a couple thousand, I think, for the jet. So this is, I believe, 60 million cells. No, maybe 30. Well, I think it's this is 512 to 56 to 56, which would be 30 million cells. So it's a reasonably small simulation compared to, for example, this liquid jet process I showed was a couple of billion cells. So we're just brute forcing our way through that. We have a scalable code. We can run on 10, 20, 30, 50,000 cores. So we request the time, and then we don't worry about this for that. We're simply using resources and see. So we're kind of avoiding the issue.
Right. I think I would like to finish the public portion of here because I know that they're very hot, but we can continue the discussion process. So thanks to